try this again. Here's another video. I recorded this already, but for whatever reason, the computer crashed twice. So this is class 6 and is the second example where we're going to use a strain gauge to, we're going to try to find out some information from a strain gauge. So we have this hollow shaft with an outside diameter of 57 millimeters and an inside diameter of 47 millimeters, and it's got a torque applied to it. And it's made out of aluminum with a elastic modulus of 70 gigapascals and a Poisson's ratio of 0.33. There's a strain gauge that's attached to it with a 55-degree angle. And that gauge reads a negative 1,400 microstrains. And we want to find the torque that's applied to this. Now, this is a very practical type of problem, a real-world type of thing. And so let's go through and see how we might go about trying to find this. Okay, so first off, we have only a single gauge. We don't have a rosette like we did in some of the other scenarios. So let's see what we can find from this rosette. So here is the strain gauge equation, if you will. We just have to write it for one gauge. Most of the time we might be writing it out for 3 gauges. Is usually the minimum required when we have a plane stress scenario. But right here, let's just take a look at what we have. Now we have, this is what we're going to measure, and here's the things we would want to know. But let's take a look at our loading situation. We're told there's a torque on there, but what other loads? Unless we were told, I don't think we could find an axial stress on here. So there's no load in the axial direction. So, and this is not a pressure vessel, even though it's hollow. So there's no stress in the X direction. And there's no stress in the Y direction, because once again, it's not a pressure vessel. If it were a pressure vessel, then it would have a hoop stress in that Y direction, but there's none there. So I say that these both, from observation, must be equal to 0. But we want to know, what is are these strains also equal to 0? Well, if we just look in the X direction and see for plane stress, for biaxial stress situation, we would find this equation to relate stress and strain. And we could see that if X and Y are 0, this too has to equal to 0. And a similar thing would take place. So we could come to the conclusion that both the stresses in the X direction, strains in the X direction and strains in the Y direction are both 0. So what we're left with is that the strain in the G is just going to be gamma xy cosine of theta sine of theta. So plug in some numbers in there. We get 1,400, and they gave it to it as negative. Gamma xy cosine of 55 degrees and sine of 55 degrees. And what we end up finding is our gamma xy, well, it's going to be negative. No way of getting around that. And so that ends up being, I think, well, I'm gonna take out the micro, right? So we could have made this e to the minus 6. So if we had done that, we get 2.980 e minus 3 radians, right? Or 2,980 microradians would have been the answer had we not put a if I didn't say I'm going to put an e minus 6 in there. So for shear, we know we need the modulus of elasticity, but modulus of rigidity, but we were only given the Young's modulus and Poisson's ratio, so we need to use this relationship right here. So we get 70, these are gigapascals, and 2 and 1 plus 0.33. So we're left with 26.3 gigapascals is our modulus of rigidity. And we know that the relationship for our xy right there is going to be G times gamma xy, right? So this is Hooke's law for in shear. So we have 26.3 e to the 9, right? That'll get us in into newtons per meter squared, right? That's 1 billion pascals, so that'll give us in pascals, which is a newton per meter squared, and we'll multiply it by our negative 2.980 e minus 3, and what we'll find, and I'll write it out this way, 78.41 e to the 6, but I'm going to turn it into megapascals, right? So that's what the result of that's going to be. I just skipped dividing by 1 e to the 6 as part of that. So that's the stress, right? So we know the stress now, but we were asked for the torque. So what kind of relationship do we know exists? We know that tau is going to be equal to TR over J. So we could find the torque if we know the stress. We just found the stress, so we could find what the torque is going to be. J, by the way, would be, we could find that with the outside, I make that mistake a lot. I write that a lot. It should be the fourth, right? So this is for a hollow tube right here. And if we have put the 57 millimeters in there and the 47 millimeters, but I would put them as meters, we end up with 5.573 e minus 7 meters fourthed. So we say T, and I'm going to ignore that minus right in there. By the way, you notice it didn't matter to me which direction the shear was going. I just wanted to know what the torque was going to be on it. And so I get my tau J R, I guess I'll put an XY right in there. And so we have 78.41 E6 times my 5.573 E7 divided by, now it's on the outside, so the diameter was 57 millimeters, so that's 0.057, but make sure we divide it by 2 because it's actually the radius, and we find that the torque was going to be equal to 1,533 Newton meters. And so what we have right there is a torque meter. Now on board ships, I would often have to do this and attach some strain gauges onto the shaft and measure. They need to actually have these telemetry little units because the wires can't be connected to the thing, so you need to actually measure these strain gauges with a little box that you duct tape to the thing that also spins with the shaft, and then you have to have a little pickup thing. And these are very sensitive units, pieces of equipment, and it's very difficult to get an accurate reading of those. So it's one of the inherent natures of being an engineer is that you'd like to have really good measurements. You'd like to trust the measurements. But there's always going to be a certain amount of uncertainty that's going to be inherent in taking those measurements. But it is a necessary thing to do because we can't necessarily measure the loads. We can't measure the stresses, but we can measure the strains. So we have to go back and go through this sort of process to be able to find out information that we need. And in this case, on a ship, we want that torque because that torque times RPM on that shaft tells us what the horsepower is at that at that location, right? We can measure what it's delivering to the propeller after it goes through the engine. The engine produces the power, goes through the transmission, and there's some losses. And then we want to find that shaft horsepower. We need to get that shaft torque. And it's a difficult thing to measure and to be very certain that you're got accurate information. Another thing that's interesting about this setup right here, by the way, is that we could also, and you'll see that in a previous version of this video, I started talking about this, but then it died. Another way that we could have actually measured the torque in this is if we had like a reference line here and here, and we were able to measure the amount of angle of displacement from that reference line right there. We would be able to establish, that would be the amount of twist that would be taking place. And then what we could do is we could find theta, that twist, TL over JG, right? So we would be able to find the torque if we knew what that angle was. So that's another way that we could get maybe a torque meter. But measuring precisely at those changing angles is the real big challenge. If you do it over a longer length, that could help, but measuring stuff in the real world is tough. But this is a real practical problem, and I like those because we're engineers and we want to do practical problems and solve real things that are going to matter to us. So hopefully this video will upload. Woo-hoo. I think I'll do one more example.